in classifying BG in BG. Okay.
So thank you very much for the invitation. It's a pleasure to be here in Vienna once again, right now with more people than the first time with the COVID. So what I want to talk today is a joint work with Daniel Alvarez and Henrique Bursztyn. And well, I hope that will be adequate and of your interest here. I will not talk about field theories, or not so much. I also will not talk about any physical motivation. This is just Lagrangians on a symplectic manifold, but, well, if you want, higher. And there are relations with physics that I will try to explain in the examples. And basically, the plan is just give a motivation. That is the one case. Then I will explain the BG case. And third, I will give examples and applications. So the only thing that I need for this talk is the notion of a groupoid that I think that you already know. So I just need two preliminaries. One is a Lie groupoid that I will denote basically by G1, G0. And then on the Lie groupoid, the most important thing is the double the RAM complex. That is given just by, giving a groupoid. I have an associated simplicial manifold that is Gn, where each of these n are the set of n composable arrows. And then associated with that simplicial manifold, I have the double complex where delta is the simplicial differential associated with that simplicial set, and D is the RAM differential, and therefore, since this is a double complex, I have a total complex that is delta plus minus I to D. Yeah. Sure. Great. So that's the only thing that I need about basically Lie groupoids, the RAM double complex. And the second preliminary that I need are current algebroids and the two current algebroids. That, I try to say normally that I don't work in higher things, just in two things. So basically, it happens that all my life turn around to current algebroids and how useful they are. So if you don't know them, don't worry, because they are not useful. But it turns around that they could appear anywhere in your life. So the only thing that I want to say here is that a current algebroid in general is just a vector bundle with a non-degenerate symmetric pairing, a bracket, and an anchor. And the special thing is that the bracket is not skew symmetric. Non-skew symmetric, but the skew symmetry is controlled by the other two objects. E2, E1 equal to what? Rho star D of E1, E2. So that's the main feature of these current algebroids. And the only two examples that we will meet today is one, what is called the exact current algebroid. And those are just, I have a manifold with a 3 form, and this 3 form is closed. Therefore, my vector bundle is T plus T star M. And this current algebroid, well, I will denote it in this way, THM. And then the pairing here, X alpha Y beta is just alpha Y plus beta X. And the strange current bracket, that is the whole mystery, is just the Lie bracket of vector fields, and then the Lie derivative along beta minus the contraction of d alpha plus the contraction with our 3 form. So this term here is what makes the current bracket non-skew symmetric and what makes the current bracket interesting as well. It happens that current algebroids appear naturally in the literature as doubles of Levi algebroids. That was the historical motivation for introducing the general definition. And also because this bracket codifies many integrability properties as, the Poisson bivectors or things like that. And the second kind of current algebroids that we will meet is an exact one, TM, plus a Lie algebra that here I'm extending G to the trivial vector bundle over M. So G is a Lie algebra. And is moreover, it is a quadratic Lie algebra. So it's a Lie algebra plus an ad invariant non-degenerate symmetric product. So in other words, I need to think that this Lie algebra can be a Lie algebra endowed with a killing form or something like that, or the Lie algebra of a compact Lie group. Those are examples of this. And here, the pairing is just the usual pairing, but with minus in the second component. So let me denote by X alpha E Y plus beta plus E prime is equal to alpha X, alpha Y, beta X minus E prime. And then the bracket is just this bracket plus the usual Lie bracket on the G component. So the Lie brackets are not mixed. So this is an example of what is called an exact current algebroid. This is an example of what is called a transitive current algebroid. So those are the two prerequisites of today. And basically, what I want to answer to give the motivation is the following question. So given a symplectic manifold M, so how to produce new symplectic manifolds? And well, the answer is basically that the easiest way to produce new symplectic manifolds, no one, is just by reduction. No? And here the answer is reduction. So the usual setting is Hamiltonian reduction. So I have a Lie group that acts on my symplectic manifold, and it have a moment map to the dual of the Lie algebra. And then, given that, I can produce a new symplectic manifold that is just the inverse image of some element here, mod out the stabilizer of that element. So this thing, that is the classical Hamiltonian reduction, have an interpretation in higher terms that is clarifying to understand other ways of producing symplectic manifolds. So let me give a reinterpretation. And this is basically Kalak and Safronov. So what it happens here is that I can produce the following diagram. So for my symplectic manifold, I have the action groupoid here that now I can put it inside, sorry, this is just a morphism with the moment map, and here is identity G times the moment map into the action groupoid that is just the cotangent groupoid of G acting on G star with the quad chain representation. This is isomorphic to the cotangent of G. And it happens that here I have a symplectic form. So this is a symplectic groupoid that have here a symplectic form on this, the RAM double complex. That form have total degree 2 because live on one, have total degree 3, sorry, because it's a 2 form on degree 1. It have total degree 3. And then what it happens is that the properties saying that, well, because it's a 2 form living on something in degree 1. It's the arrows. It lives in the arrows of the groupoid. That in terms of the simplicial manifold here, it is 1. Therefore, it's a 2 form living in degree 1. Then if you want, this is why we call it one-shifted symplectic. Because the 2 form, the symplectic 2 form live in degree 1. So this will be an example. This is Kalak and Safronov.
Safronov.
So what it happens is that this is a one-shifted symplectic groupoid. So in fact, this is a usual symplectic groupoid. And here, the properties of saying that this is a moment map, it's saying that this is a shifted Lagrangian inside this shifted symplectic groupoid. I will tell you in a moment. And moreover, it have another one. There is another Lagrangian given by the quad-joint orbit with the usual KKS symplectic form. And here, this is the groupoid, is just the pullback groupoid. And this is another Lagrangian. And then the symplectic manifold M epsi, it appears as the Lagrangian intersection of, normally these people from derived geometry denoted this as this thing. And this is Lagrangian intersection. That is just a fiber product of stacks in this case. Okay, so the takeaway of this picture is that Hamiltonian reduction can be reinterpreted as a Lagrangian intersection inside a one-shifted symplectic groupoid. Yeah, so I'm going to that. So what are all these words?
Here in form don't need derived intersection in this picture.
I will explain later which kind of intersection I will consider. Yeah. So let me give precise definitions of all these things. So a one-shifted symplectic groupoid is just a Lie groupoid here And now I have a 2 form in the level 1 in the arrows of the groupoid, and I have a 3 form in the objects of my groupoid, and they satisfy that they are close. So for the total differential, that is that one that I explained it over there. And now, so a symplectic manifold is something that the form is closed and non-degenerate. So what means non-degenerate? It means the IM form, yeah, that's completely right. Thank you. So delta is the simplicial differential. So this is a simplicial manifold. That means that I have a phase maps di going from Gn to Gn minus 1, and delta is just the sum from I equal 0 to n to the pullbacks of these things, because this is acting on forms. And yeah, sorry. The alternated sum. And now, what it means that is non-degenerate? Well, it happens the following. It happens that I have the Lie algebroid of my groupoid, and now I have the anchor going to TG0, and then it happens that this 2 form, omega 1, it produces a map that goes from the Lie algebroid to the cotangent of G0, and this is the dual of the anchor, and here I put just the dual of that map. And I'm saying that it's non-degenerate if this thing is a quasi-isomorphism. Okay, so in other words, what we are saying is the following, is like the complex AG rho plus lambda omega TG0 plus T star G0 going to rho star plus lambda omega star of A star is exact. And that's equivalent. So this condition at the infinitesimal level, together with this one, is equivalent to say that AG, the Lie algebroid of my groupoid, inside the current algebroid twisted by the 3 form that I have here on G0 is a Dirac structure. And I forget it to say here, what a Dirac structure on a current algebroid is just as a bundle of my current algebroid with dimension of L equal to 1/2 of the dimension of E. And, well, probably we are talking here of ranks of vector bundles. And then I have that the sections are closed for the Lie bracket, and then I also have that is isotropic. So in other words, these 2 conditions is say that is maximal isotropic, and this that is involutive for the Courant bracket. That's a Dirac structure. So in other words, one-shifted symplectic groupoids are the same as the objects that integrates Dirac structure on an exact Courant algebroid. Okay? Dirac structures on an exact Courant algebroid. Well, because it's global, no? The groupoid. So if I have a Dirac structure on an exact Courant algebroid, so if I have a symplectic groupoid, its Lie algebroid, a one-shifted symplectic groupoid, its Lie algebroid is exactly a Dirac structure on an exact Courant algebroid. Well, it's not one-to-one because not every Lie algebroid can be integrated, but whenever it can, that's the case. The source simply connected one always inherit a one-shifted symplectic structure. Sorry.
Omega, did you define it? Is it just what you get from differentiating the omega 0?
Yeah, so you can think, in other words, you can think that the first condition there of being close is telling you that delta omega 1 is equal to 0. Therefore, it's multiplicative. That means that you can think it as a groupoid morphism between the tangent and the cotangent. You differentiate it and you obtain that thing. Yeah.
Non-degeneracy condition is somehow cohomological. Right?
Exactly.
What does it mean in terms of the Fischer-Deram complex?
In other words, what I can tell you is that a groupoid, it have a tangent groupoid and it have a cotangent groupoid. And what you are saying is that this omega 1 is a morphism between the tangent and cotangent. What you are saying is that it's a Morita map. So it's a quasi-isomorphism between the tangent and cotangent. And now let me explain what a shifted Lagrangian is. On a one shifted symplectic groupoid. Well, this is a groupoid morphism x1, x0, and then I have phi 1, phi 0 into g0, g1, and I have as well beta that is a two-form on x0, and then it satisfies the following, that is that the pullback of omega 1 plus omega 0 is equal to d beta. And this is called isotropic condition. And then the Lagrangian condition. No, it's just a groupoid. This is just a groupoid, and it has a two-form on the base. So I have my shifted symplectic groupoid, so I have here my omega 0, my omega 1, and I have here a beta. Those are the things that I have. This is shifted symplectic, and this beta, it satisfies this equation here. When I pull back this thing, in terms of cohomology, is 0. And then the Lagrangian condition, it means that A of x go into rho of x plus Li phi, P of x0 plus AG, PG0. This is T phi, go into 0. So this is the mapping cone of the tangent of this morphism here. And then I have zeros here. I have the cotangent here. And this is rho star x. And this is beta sharp plus P star phi composed with my lambda omega. And this is Li phi star composed with lambda omega star. And what I'm asking again is that this morphism here is a quasi-isomorphism. That's the Lagrangian condition in this case. And then the property that this thing satisfies, that is the important thing, is that given two Lagrangians, if I have x, that is basically the stack represented by these things, and then I have another Lagrangian y, then the fiber product, this is a zero shifted symplectic manifold. So in other words, I can think this as a groupoid endowed with a basic two-form that is transversally non-degenerate. And this was studied by Hoffman and Sahamar. Really recently, there is a whole development of this zero-shifted symplectic. So which kind of things this unify? Sorry?
Half of run condition, right?
This quasi-isomorph is something that is telling you that somehow is maximal isotropic. It's telling you that the tangent to the cotangent shifted by one, it is a quasi-isomorphism. But here you are using the mapping cone as the tangent.
Was it already like this for zero-shifted Lagrangian?
For zero-shifted Lagrangian, it will appear just that Tx, so TL going to T star L is non-degenerate. So for zero-shifted, it's quite easy to make. So let me say the last thing. So what's this unify? So I have M, and what I say is that if I have my moment map to G star, this is Hamiltonian reduction. If I have the moment map to a general Poisson, and then I assume that this Poisson manifold integrates to a symplectic groupoid, this is Mikami-Weinstein reduction. If what I have is a dual Poisson Lie group, this is dual Poisson Lie group, then this is Lou-Weinstein. What?
Maybe you can write a bit smaller.
Yeah, I can try. If I have G with the Cartan-Dirac, then this thing is the AMM quasi-Hamiltonian groupoids. And in general, if I just have a Dirac manifold, this is the general picture that I'm presenting here. This is the general picture. And this was studied, for example, by Bursztyn and Henrique, or by Ping Chu, among others. Yeah, I can try to make it. So this is basically the one-shifted case, and this explains how one can construct symplectic manifolds by using basically Hamiltonian reduction in a wired way, or many types of Hamiltonian reduction. So right now, if you want, one of the questions is, instead of producing symplectic manifolds, can we produce? How can we produce? So the new question is, yeah, so the general construction is this one. So it means that once I have a one-shifted symplectic groupoid and two Lagrangians inside it, you can produce a symplectic manifold, more or less.
Is it symplectic really, or something structure-like?
It's more or less something that it's a manifold with a foliation that is symplectic in the transverse directions. That's what it is.
How this graph makes this construction
special? So in this case, the groupoid that you need to use is the cotangent bundle. Okay? In this case, the groupoid that you use is the symplectic groupoid integrating a Poisson manifold. Okay? And here you have an action groupoid, and here you can pick whatever orbit of this groupoid as it happens on that case. In this case of the dual of the Poisson, you also use the double, so this was make it, so if you have a Poisson, there is a double symplectic groupoid. So you use this part of the double symplectic as the one-shifted Lagrangian. In the Cartan-Dirac, you use G acting on G with the conjugation, and it happens that the Cartan-3 form becomes a Dirac structure there that is precisely the Dirac structure that makes, over there, that makes that Dirac structure over there. In this case, I cannot say it right now, but I can give you the reference or the original article by Alexeyev, Miquel, Henrique of the article by Pingshu that is called moment maps.
The wedge product of the left and the right invariant power Cartan forms. And kind of like
not in this model.
It's actually the expression of what you said.
Yeah, it's a bit more difficult. I don't remember right now. And for a general Dirac manifold, well, you expect to be integrable. If it's integrable, then you have a one-shifted symplectic groupoid integrating it. And then the Lagrangians, what you use is, it's always more or less the action groupoid, but in general, you can use whatever other Lagrangian that you want over there. So right now, the question, if you want, is how can we produce one shifted symplectic groupoids? And the answer is as intersections of two shifted Lagrangians. Okay, so in order to explain that, I need to explain to you what are two shifted symplectic groupoids and what are two shifted Lagrangians. So, yeah.
This lambda omegas is, this omega is omega 1, right?
That omega is omega 1, yeah, that's right. It just depends on omega 1.
And it's just musical isomorphism on G1.
Yeah, so if you want, think in the following way. So omega 1 sharp, it's something that it's a vector on TG1, and then it gives you a covector on TG1.
Okay, it's fine.
Okay, then what you do is, to show it in the Lie algebroid, here, you just can include whatever element here. So let's say it in this way. Any element of the Lie algebroid is inside here. But right now, to see an element on TG, here, what you do is you use the unit. So then you use the unit of an element in TG, let's call it X, and that is what produces you lambda omega of AX. Or if you want lambda omega per it, yeah, anyway. Maybe there is a factor of 1/2 or something like that, but yeah. So I don't want to explain you what a two-shifted symplectic groupoid is, but I just will give you an example that is BG. So what I will have is the setup. is G, a Lie group, plus I have my ad invariant non-degenerate pairing. On my Lie algebra. And then I can produce this omega 2, that is exactly what Dima was mentioning, the pullback of the left Maurer-Cartan form and the pullback of the right Maurer-Cartan form, that this is a 2 form on G2, that is 2 copies of G, of my Lie group. And then I have a 3 form that is 1/12, probably there is a minus here, the Cartan 3 form. And what I claim is that this satisfied that is close for the total, sorry, this is 2, but this is 1. I have 2 plus 1 equal to 0. And then the I form, the IM form, in this case is lambda omega again, that goes from G to G star, and it happens to be just the contraction with the pairing that you choose here. And clearly, since this is non-degenerate, since this pairing is non-degenerate, this is non-degenerate and therefore deserve to be called a symplectic form. Okay, so in other words, for those people that know current algebroids, that they are here, a current algebroid is the same as a degree 2 symplectic Q manifold. Q manifolds are conjecturated that they integrate to n groupoids. So degree n Q manifolds integrates to n groupoids. And the symplectic form should integrate to a symplectic form on that groupoid. And that's what it happens here. What we have is a current algebroid over a point that is little g with the ad invariant product. And the integration of the current algebroid over a point is exactly the Lie group with this 2 shifted to form, symplectic form. Okay? And so why I'm calling this BG? Because the stack that this groupoid represents is exactly BG. So the principal bundles over G, and you can think, if you want, that this shifted form on the groupoid, it represents a shifted form on the stack. But working with the stacks, it has the problem that you lose all the geometry, or it's more difficult to do geometry. So what I'm giving to you is a concrete realization, a concrete symplectic realization, geometric, of that symplectic stack. And yeah. This is a 2 shifted. The other is 1 shifted. Yeah. And therefore, right now, the question is, what are Lagrangians there? Definition. A shifted Lagrangian groupoid on, let's denote it just BG, but by BG, I'm really referring to this Lie groupoid with this concrete model here, with the 2 shifted symplectic model there. Is a groupoid morphism again, x1, x0, I have my phi, now I have here G a point, and now what did have this with? Well, I have On the level 1, I have a 2 form. And on the level 0, I have a 3 form. So if you compare with that definition here, everything is shifted by 1, because this is 2 shifted while this is 1 shifted. And now, which are the properties? So isotropic. So that means that the pullback of this thing is d of beta blah plus beta 0. And the 2 Lagrangian, that it means that the Lie algebroid go in. So this is the tangent complex of my x, and now I add here G, that is the tangent complex. I have here Lie phi, and then what I have? T star of x0, I have the contraction with my beta, and here I have the cotangent complex of my x, and here it is lambda beta star plus Lie phi star composed with lambda omega, where the lambda omega is just basically the pairing. So this is a quasi-iso. So what we have here? Well, in the row upstairs, what we have is the mapping cone of the tangent of this morphism. And here I have the cotangent, and this shifted by 2 minus 1, that is 1. While here the cotangent is shifted by 1 minus 1, that is 0. So there is a general rule. So these definitions can be done for any degree. The problem is how many examples of those objects we have. But anyway, so this is the main definition of today. So what a shifted Lagrangian groupoid on BG is. And right now what I want to give you is the motivation and basically examples that explain why to look into these objects. Okay.
For the special case BG and not for a general groupoid?
Well, you can do it. Now, what I'm telling you is if you have a group, all the examples of 2 shifted objects that you have are these ones. If you have a groupoid, I know some examples of 2 shifted symplectic structures there, but basically almost no one. So basically the problem is that it's difficult to construct examples. You can do it in general, but then the problem. Yeah.
Here, which is a 1 form on G0.
No, will be a 4 form.
4 form on G0. Yeah. The other.
Yeah, you can do it that.
The first contraction classes.
Yeah, so something, okay, so let me give this example. If I have, now I need this. So suppose that I have one of these groups with a quadratic Lie algebra at the infinitesimal level. Then I can look into a G principal bundle for that. So
it's kind of like the pre-quantization of this BG is this 2G, right? But I don't know any nice 2 groupoid in that case, right? So
let me say this. Suppose that I have G as before, and then I have a principal bundle for that G. And then I can create the gauge groupoid, so with base, let's say it B. And then I can create the gauge groupoid of that thing, GP over B. And it happens that this groupoid is Morita equivalent to G. Therefore, one can translate the two-shifted symplectic structure here under this Morita equivalence to the two-shifted symplectic structure, to a two-shifted symplectic structure here. So in the base, in the B, what will appear? It will appear the first Pontryagin class that is a 4 form on B, once I translate that of the principal bundle that I choose. Okay, so let's go to the main properties. So the first main property is that if I have that is shifted Lagrangian, then it is really easy by just picking Euler characteristic of these two complexes to observe that the dimension of x1 minus twice dimension of x0 is equal to 1/2 of the dimension of G. So in particular, just even dimensional have shifted Lagrangians. So in other words, not any, so you know, if I have a symplectic manifold, I have Lagrangians there by the Darboux theorem. But here it happens that not every two-shifted symplectic groupoid, it have shifted Lagrangians inside that. There is dimensional constraints, for example. That is quite surprising, I think. Second, the following are equivalent. The following are equivalent. This one, this x1, x0, beta 1 plus beta 0 inside phi G is shifted Lagrangian. The second is that A of x inside of the current algebroid twisted by beta 0 plus G using the anchor of x plus lambda beta plus Li phi is Dirac. In other words, if I have a groupoid, I have a groupoid with this beta 1, beta 0, and phi. I have a really easy way to check when it's shifted Lagrangian. The only thing that I need to check is that the Lie algebroid embeds via these three maps into a Dirac structure in this particular current algebroid. So it's the standard current algebroid twisted by beta 0, and then I add this current algebroid G over a point. Is the differential of this map that goes from the Lie algebroid A of x to G. So in other words, I can use the converse statement. If I want to find shifted Lagrangians, the only thing that I need to find is Dirac structures here and integration of those Dirac structures. So basically what I have here is a Dirac structure on a transitive current algebroid of a particular kind, but basically any Dirac structure on a transitive will give me some of the shifted Lagrangians that I want to have.
Quite a severe restriction, like all the SUNs, they're R-dimensional.
What? Oh, yeah. This is super hard condition. But it is what it is. We cannot do anything. Okay, so let me give more properties. Now, just a follow-up of what I was saying. Assume x1, x0 is source simply connected. And so what I'm assuming is that I have, this is a shifted Lagrangian, this is shifted Lagrangian, and moreover, I'm assuming that it's source simply connected. And now I choose a complement for the Dirac structure over there. So AX plus some L equal to my T of beta 0 x0 plus G. So choose a complement. Therefore, this is a current algebroid, and it splits as one. One is Dirac, the other is just a complement. Therefore, what it happens is that A of X become a quasi-Levi algebroid. And now, since I'm assuming that this source simply connected, the groupoid, it happens that x1 over x0 is a quasi-Poisson groupoid. So this is a theorem in derived symplectic geometry that says that an n-shifted Lagrangian inherits an n-1 shifted Poisson structure. Here at the level of groupoids is not true anymore. You need to make choices. The choice is the choice of a complement, and it's not always true that the quasi-Levi algebroid structure at the infinitesimal level can be integrated to the groupoid. But in favorable cases, you can do it, and that's the case that we have. And then let's make it the most important property, that is the Lagrangian intersection. So suppose that I have x1 beta 1 over x0 beta 0 entering into G, and then I have another one, y1 gamma 1 over y0 gamma 0. So these are two Lagrangians, and assume that these maps are transversal. Then the theorem is that x1 over G, y1 over x0, y0 is a one-shifted symplectic. Groupoid. So which are the forms? Well, the two form is just beta 1 minus gamma 1, and the three form is beta 0 minus gamma 0. And it is easy to see the Dirac structure on, so I say that this is a one-shifted symplectic, so the infinitesimal is a Dirac structure on this current algebroid. And understanding this Dirac structure is easy in terms of current reduction, because this basically gives you two Dirac structure on this kind of current algebroid, and then they are transversal. You can make Dirac reduction with respect to the common factor here, and then it gives you a Dirac structure over here. That's what is integrating. Okay, so in the last 5 minutes, let's try to give some concrete examples of these Lagrangians. Okay, so the first example is when G is a point. If G is a point, it satisfies this definition. It happens that infinitesimally, I just looking into Dirac structures on an exact current algebroid. Therefore, this satisfies that two Lagrangians on a point are the same as one shifted symplectic. And that's also well known. So, in other words, any Dirac structure on an exact current algebroid, the integration of that gives you a Lagrangian on a point. The second example is just if I have a group entering on G, then it happens that H Lagrangian if and only if the Lie algebra is Lagrangian. So that means that dimension of H is 1/2 of the dimension of G, and HH is equal to 0, and this is a subalgebra. So in other words, Lagrangian subgroupoids are the same as basically a one-to-one modulo source simply connected integration with Lagrangian subalgebras. And what happens is that once I choose a complement for these Lagrangian subalgebras, the H become a quasi-Poisson Lie group. And that is one of the informations that I have here. The third example is the arrow groupoid. Arrow groupoid. That it is this groupoid here is, I know that is confusing, but in the base of the groupoid is the arrows of my original group, and here is the space of 3 composable arrows. So I denoted this as X, Y, Z, X, Y, Z, and this is the source of the groupoid, and this is the target. And multiplication is just composition, vertical composition of squares. This is also called the groupoid of squares sometimes. G3 here in the arrows is G3. Sorry? The arrows go this way. And then it happens that if G, so if I take my G that is symplectic, then beta 0 is omega 1, beta 1 is 1/2 of X star theta right, X, Y, Z of theta left, plus Y theta left, Z theta right, and it happens that GI is Lagrangian inside basically 2 copies of BG, this with the opposite symplectic structure. And why is this important? By the following theorem. Let me make it probably here. So I'm finishing. Because given two Lagrangians, so this is a theorem, given x, y inside the G Lagrangians, then I can make x product y entering in G. So here I change the orientation, and then I put here GI, and it happens that this is a Lagrangian entering here, this is a Lagrangian entering here, therefore and it happens that these two maps are always transversal. It doesn't matter whatever I put here. So this is always transversal, and here the map is YZ, and this is phi times psi, the two Lagrangians, and then this fiber product. So the fiber product of these two Lagrangians as here, it gives you the homotopy fiber product. So in other words, the homotopy fiber product of Lagrangians is always well defined, and give one shifted symplectic groupoid. Okay, so let me finish with mentioning other examples, and since I'm over time, I just will mention them. So if I have other examples, are given by one, by quasi-Poisson, DG manifolds, so suppose that, so this is just, I have a Lie quasi-bialgebra, and this is the dream field double of that Lie quasi-bialgebra. And this is the bialgebra. So this is the quasi-differential on the bialgebra, and then the Poisson satisfies chi, and this rho is the action of G into the vector fields of my manifold. F, it goes from G into two copies of G, and chi is an element on the wedge. So G is a Lie algebra, this is the quasi-structure of bialgebra, and this is a quasi-Poisson manifold. So it happens that this defines a Dirac structure inside of T rho chi of M plus partial. So therefore, an integrable quasi-Poisson manifold integrates to a two-shifted Lagrangian on D. So which are examples of this thing is a Poisson Lie group acting on itself by conjugation, for example, or then a compact connected oriented surface with boundary, then the space of the character variety of that, it's also an integrable quasi-Poisson manifold that was doing by Anton, Yvette, and Eckhart, or more generally, we can decorate surface and make fusion on them to obtain Lagrangians. And then if I have a Lie group and a subgroup and then a solution of the classical dynamical Young-Buster equation, It's also give me a two-shifted Lagrangian on D. And yeah, I think that I'm over time, so that's everything. Thank you for your attention.